guys. So today we continue our discussion of application of Maxwell equations. In particular, we are going to use some equations from this system in order to show how we can determine speed of light. So in this case, we will consider so-called linearly polarized electromagnetic wave. So how we define it? So if we have some system of coordinates, so it will be x, z, and y. And let me change the color. We consider here the direction of electromagnetic wave propagation. C vector is like velocity vector. Then we have, we have electric field vector E and magnetic field vector B. So when it's obviously that electric and magnetic field vectors are perpendicular to each other. However, when we align them in that way that they are parallel to axis y and axis z respectively, we can consider that we deal with linearly polarized electromagnetic wave, which travels along axis x with speed like velocity c. So in this case, electric field vector and magnetic field vector. Let me change color. These guys will be function of x, position along axis x, and time. So this will be another function of x and time. So, so they will not be functions of y and z. So now we can consider two equations from system of Maxwell equations, in particular Faraday's law. Faraday's law tells us that integral over closed path of scalar product of electric field vector and ds vector will be equal to minus dfb over dt. And another equation which we are going to which is actually needed for this derivation, that will be Maxwell Ampere's law, which is the fourth Maxwell equation, and that will be integral over closed path scalar product of magnetic field vector times ds vector, and that should be equal, it has two components as we remember from previous discussions, mu naught times I, conductivity current contribution, and Maxwell displacement current contribution, which is epsilon naught mu naught times df E over dt. So here we have P, magnetic field flux, and here we have electric field flux. First derivative over time. Assuming that we deal with free space, means there is no electric conductivity current, so this term can be considered as zero, so we will not deal with it. So taking this into account and all these conditions of linearly polarized electromagnetic wave, it is possible to go through the analysis of and modification of these two equations in order to get the following expressions for electric and magnetic field. So we have second partial derivative of electric field over x position, which partial because we have two variables, x and t. So this is the second partial derivative over position x will be equal to mu naught times epsilon naught, second partial derivative of electric field over time. Similar, we can write also for magnetic field. So this is partial derivative, second partial derivative of magnetic field over dx square. That is equal to mu naught times epsilon naught times second partial derivative of magnetic field over time. So we get these two equations for electric and magnetic fields. They can be kind of related, obviously, because we have relationship between magnetic and electric field in electromagnetic wave. But what is important here that these equations have the form of so-called general form of wave equation. And if you remember from physics 1, we considered such equation. So general form for wave equation, we consider that obviously in the scope of mechanical waves, but that actually applies in general case for all types of waves. Second derivative of position along axis y over x square, the x square, so partial derivative, second partial derivative is equal to 1 over v square, where v is the speed of wave propagation, times second partial derivative of y over time square, dt square. So taking this into account, this general form of wave equation and equations which we got for electric and magnetic field, we can come to the following conclusion. First of all, if we're talking about electromagnetic waves, so obviously this v, the speed of propagation of wave, should be equal to c, which is speed of electromagnetic wave in free space in vacuum. So that's why we can write that c, when we consider this equation, similarity between these equations, speed of electromagnetic wave propagation in free space should be equal to 1 over square root of product mu naught times epsilon naught. And these guys, permittivity, like magnetic and electrical permittivity of free space, these are fundamental constants, means that speed of propagation of electromagnetic wave in free space is also a fundamental constant. So if we substitute here the magnitudes of this mu naught and epsilon naught, we will get for speed of electromagnetic wave 2 times 99792 10 to power of 8 meters per second. So this is the fundamental constant, speed of electromagnetic wave in free space. What is important that experimentally was measured speed of light, like visible electromagnetic waves in the visible spectral part. Um, at that time, it was not clear if light is electromagnetic wave or not, but the fact that speed of light in vacuum uh, is equal to this number, or measured to be very close to this number, uh, was a clear evidence that light actually is a form of electromagnetic wave. So it's kind of an important finding. So now the solutions for these wave equations, which we got for electric field and magnetic field, can be written in the following form. So for electric field, we can write, and this is E maximum times cosinus kx minus omega t, and magnetic field is B maximum cosinus kx minus omega t. So here we have E maximum and B maximum. These are amplitude values of respective electric and magnetic field. Then K, you should know what is K, but as a reminder, that is wave number. So that is 2 pi over wavelengths lambda, and omega omega, some lagging in writing, is angular frequency, that is 2 pi times f, where f is frequency. So now the ratio between angular frequency and the wave number, omega over k, that is 2 pi times f over 2 pi over lambda, that is equal to lambda times f, and that is speed of electromagnetic wave propagation, or in general, that could be considered as speed of wave propagation. But in scope of our discussion, that is speed of light actually in free space. So now let us take derivatives of electric and magnetic field expressions, which we highlighted here, with respect to position x and t. So we will take partial derivative of electric field over x and partial derivative over b over t. So let us write it here. dE over dx will be equal to minus k times E maximum times sinus kx minus omega t. So for magnetic field, we take partial derivative over time. That will result in omega times B maximum times sinus kx minus omega t. Okay, now in the process of this obtaining these wave equations for electric and magnetic field from two equations from a system of Maxwell equations, it is possible to show that first derivative of electric field over, like partial derivative over electric field over position x is equal to minus partial derivative of magnetic field over time. So taking this into account, coming back to our derivatives, we actually can write that K times E maximum is equal to omega times B maximum, since they actually are equal to each other. So now the ratio between amplitude of electric field and magnetic field will be equal to omega over K, and as we already know, that will be equal to c, speed of light. So it's also possible to apply for not only for amplitude values, but any like values at any moment of time, instantaneous values of electric field and magnetic field. So in general, we can write that the ratio between maximum electric field to maximum magnetic field will be equal to the ratio between electric field and magnetic field instantaneous values at any given moment of time, and that will be equal to c, speed of light. So that's important feature of electromagnetic wave, that at any given moment of time, when we have consider some electromagnetic wave traveling in free space, the ratio between magnitude of electric and magnetic field will always give us the universal constant, which is speed of light in free space. So that's some fundamental feature, like property of electromagnetic wave, which you should remember along with the expression for magnetic for speed of light or speed of propagation of electromagnetic wave in free space, which we can remind here, which is c equals to 1 over square root mu naught times epsilon naught. So these are the main take-home messages from our discussion today, which highlight the fundamental features of electromagnetic wave and its propagation in free space. And we obtain them by considering two equations from 4 out of 4 included in the system of Maxwell equations. So with this, we will finish this discussion, and our next topic to be considered will be energy transferred by electromagnetic wave, which is important feature because electromagnetic wave transport in space some energy, and they can transfer quite a lot of energy. Let's say if we consider main source of light in our solar system, our star sun, we obtain a lot of energy in form of electromagnetic wave from our sun, and obviously this is an important factor to be considered. So we will focus on specifically on energy which is transferred per unit time, per unit area by electromagnetic waves. So that's our next topic for our discussion, and hope to see you next time. Thank you for attention, and goodbye.